Alright, this is going to be a short video on common ion effect. And what is a common ion effect? This actually comes from Le Chatelier's principle. It says whenever you have a weak electrolyte and a strong electrolyte containing a common ion together in a solution, the weak electrolyte ionizes less than it would if it were alone in the solution. Uh, this affects acid-base equilibrium. We'll also see later in the chapter how it affects the solubility. And let me give you an example of what common ion effect looks like, and it brings us into our next topic. If I have an acid-base equilibrium like 0.10 molar acetic acid, okay, I want to write an equilibrium for that. And the acetic acid I can just write as HAC. What it has to react with is water as a liquid. The HAC is aqueous, and some of it dissociates into Bronsted-Lowry. An acid's a proton donor. The water becomes your proton acceptor, so it's acting as an acid. Water's acting as a base, and what you get is hydronium, which is the same as hydrogen. That would be your conjugate acid from the water, and acetate, which is the conjugate base of acetic acid. Now, if I look at this equilibrium, it's capable of going in both directions. So in the one direction, as soon as you're producing H plus and AC, this can re-react at the same rate, go in the opposite direction, okay? And so you have yourself a two-way equilibrium. If I define a K for this, my K expression would equal the amount of hydronium, or you could just say hydrogen, times acetate over acetic acid. Water is not in your equilibrium because water is considered to be constant. At 25 degrees, your concentration of water is 55.6. So it's not in your equilibrium. This would be viewed as a Ka. And for acetic acid, we know what this number is. It's 1.8 times 10 to the negative fifth at 25 degrees. Okay, standard temperature. Now, if I apply a equilibrium shift to this, say I want to add to this, I'm going to add to this equilibrium 0.15 molar sodium acetate, which would be NaAC. If you actually look at it, where a lot of students get confused is they're trying to put sodium into the reaction, when in fact sodium is not in this equilibrium at all. It's not a common ion, and in fact the sodium is just a spectator ion. So the key is forget about the sodium. It's in no way affecting the equilibrium. So what we really want to do is look at the acetate. And effectively what I did is I've just increased my concentration of acetate. Now for that increase, Le Chatelier will say, take that increase and bring it back down to minimize the effects of equilibrium. That will cause the reaction to shift away to the left, okay? That's going to decrease your hydronium. It's going to decrease the initial acetate, and now it's going to increase your acetic acid, okay? If I look at that mathematically, okay, for this number to stay the same, 1.8 times 10 to the negative fifth, if I was to increase the acetate, shifting towards the products increases the denominator, decreases your hydronium, and also decreases the acetate by shifting away from that to keep your K constant. And that's the essence of the common ion effect. If I was to increase my concentration of acetic acid, you always have to look at this, it's from your initial, what was the initial stress? Because if you look at both of these, it gets confusing. You see that you're both increasing acetic acid. And whenever I show my initial increase, I always show a downward arrow. That's showing that the equilibrium is trying to bring it back down. To bring it back down, it's going to shift to the right, okay? And that effectively would increase the amount of ionization, okay? So you're going to get more hydronium, and you're going to get more acetate. Now, again, if I compare that to my equilibrium expression, increasing this initially, okay, is going to, you can't change this number, so it's going to increase your acetate, increase your hydronium, and bring the HAC back down to keep your K constant, and that's common ion effect. So let's try actually doing a problem with the common ion effect. And I'm not going to try and introduce Henderson-Hasselbalch now or buffers, but if I look at this equilibrium, let's do the problem we have right in front of us. Okay. The problem I'm going to ask you would be if you have this solution, 0.1 and 0.15, then what is the pH of your solution? Okay, the first thing is you have your equation, and whenever you're dealing with common ion problems, the thing that gets people mistaken is that the HAC and the HAC are not on the same side of the equilibrium. They're always going to be on opposite sides. And that tends to confuse people. They're trying to take the acetic acid and react it with NaAC, always get rid of the spectator ion, okay? And then we could actually look at this as an icebox, okay? I initially start off with 0.10 molar HAC, okay? Initial, change, equilibrium, okay? Initially, I don't have any dissociation, so I have 0, and you use molar in here for your units. And your AC, this is the whole trick, has been increased. Initially, it's not 0. You might be used to putting a 0 in here. It's initially 0.15. And that's what's different about common ion problems, okay? The amount, what we want to know is the amount of HA3O. Okay, let's get rid of this. Okay, so it's plus X. Once you know that's plus X, this is also plus X. Okay, because your shift is to the right because you have 0 for H3O. So here I got 0.15 plus X. For the acetic acid, it's minus X, so I end up with 0.10 minus X. Okay. Now I'm going to plug all these numbers into my K. My Ka then is equal to X times 0.15 minus X and 0.10 minus X. And the thing that's beautiful that we really hope for is that our X is insignificant. Okay, we can test for insignificance. If my K value over the initial is less than 10 to the negative third, then I'm insignificant. If I go 1.8, that doesn't look good, times 10 to the negative third over 0.10, sorry, that's a negative fifth, is less than 10 to the negative third. This number becomes 1.8 times 10 to the negative fourth, and that is less than 10 to the negative third. So I can disregard my X. In terms of the 0.10 and the 0.15, it's insignificant. Let's bring that up again now. Go back to red. Okay. So I can disregard that. By doing that, I don't have to do any crazy quadratic equation, and I'll I'll solve for my x. 1.8 times 10 to the negative fifth equals 0.15x over 0.10. Solving for x, I'm going to divide by 0.15, multiply by 0.10. Now I solve for x, which is your hydronium concentration. Keep that in mind. And quick calculation, 1.8 to the negative fifth. And that's times 0.1 divided by 0.15. So this number is 1.2 times 10 to the negative fifth molar. Alright, and now I want my pH, which is going to be the negative log of my concentration of H. So it's 1.2 times 10 to the negative fifth, which has 2 sig figs in it. So a negative log, my answer, and I get 4.92. And remember, when it comes to pH, the first number represents your insignificant figures. The second number, the numbers after the decimal, are actually a 2 sig fig, so your answer has 2 sig figs. Now, what you might notice is this did not dissociate as much as it normally would have. If you did this without the HAC, I think you get around like a 2.5 for a pH. This has shifted your equilibrium by increasing the acetate. It's pushed the equilibrium to the left, and it's lowered the amount of hydronium that you would have gotten. So it's raised your pH. And that's a common ion effect. The next thing I'm going to be teaching is how to apply Henderson-Hasselbalch to this equation.